Hey everyone. So in this video we're going to be skipping past the rest of turn in place, what I said was planned, and we're just going to go straight into the jump prediction and jumping because turn in place became something of a big issue to deal with and to finish the way I wanted to finish it without having proper ending animations for going both right and left. And if you had proper ending directions going right and left and stopping, and you end up facing forward, the current system would work as it is and it would give the intended result. But since I do not have those animations, I'm going to leave it where it's at. I think it's passable for now, and I'm going to move on to jumping. And that is what I'm going to be covering in this video. We're going to be getting started with jumping finally, one of the final parts of distance matching here. We're not going to be doing anything with the animation graph in this episode. We're only going to focus on all the logic for the prediction, which is actually all blueprint logic. Without further ado, let's begin. So I'm in my character blueprint, and it's actually going to be the only blueprint or thing we're going to be inside of for this video. We're just going to focus on setting up the logic for the prediction. The next video will be doing the actual state machines. The first thing I'm going to do is I'm going to find a empty spot, and I'm just going to type jump, and there's this action event to jump. I'm going to click on it, and when it is pressed, I'm going to jump with the jump function. And after I jump, I'm going to get a do once node, and this do once node is where we're going to do our calculations. The reset is just going to be set to released here, and completed will be plugged into a function that I'm creating now, and it is going to be called predict jump arc. And there's one more important thing in the character movement component. Make sure to go to your jump settings and change air control that value to 0. And the reason for that is if we play, I can't move around while I jump, and which means the prediction, if we do it as soon as we leave the ground with our velocity, we will always land where we are predicting. And if we make adjustments in the air, that can adjust our landing location. And that's not really much of a problem on a flat surface because we just want our z distance, our distance from the z value. But let's say we're jumping from one platform to another, and we try to adjust it and go back to fall off. Well, it predicted that we'd land on that platform and our animation breaks. So we don't want to do that, and you could get by that by doing a more complex system where you're constantly re-simulating things as the character jumps. But that's a bit complicated, and I don't want to get too complicated with all of this because I want to focus on distance matching and really getting these animations to work with distance matching. The underlying logic for the prediction can always be updated and changed and modified easily to suit whatever circumstances you need it for. So what we're going to do to predict the arc is we're going to use a predict projectile path by object type node. I'm going to drag out from here, predict projectile path by object type. The start position is going to be the actor location. The launch velocity is going to be the velocity of the character, of our actor, for both x and y. But z is going to be our jump z velocity from our character movement component. So I'm going to break this vector, and from the x on break vector, I'm going to drag out and get a make vector node. Y goes into make vector, return value goes into launch velocity. I'm going to grab our character movement. I'm going to grab our character movement component. I'm going to get jump z velocity, and that is going to be the z in our make vector. And now I'm going to make an array for object types. I'm just going to leave that at the default world static. And for actors to ignore, I'm going to get another make array node. And I'm going to get a reference from self to plug into that 0. And this is just so that no matter what happens, the trace never stops because it's hitting the actor itself. Now if I just get a for each loop, and if I get a draw debug sphere, and I'm going to set the radius to 30, let's set the duration to 2. We can see what this predict projectile path by object type is doing. Or not. We need to actually plug in our predict jump art function, or it's not going to do anything. So make sure you plug that in on your event graph into do once. And now we can see. And so you can see that the jump arc doesn't line up exactly with our predicted arc here, but the apex does. So what we're going to do to fix this is we're going to do another trace once we reach the apex, and that trace is going to just going to take our current velocity, and it's going to, for the z, add a negative 9.81 meters a second, or whatever you have gravity set to. And so that will get us an accurate stopping location. But first we have to actually find our apex to both get the distance and z from it, and also to know what we're tracing from. For now, I'm going to disconnect the draw debug sphere. We don't need to draw a sphere for every step here. And I am going to check if this array index is equal to 0. And if that is true, we are going to set a new local variable, which is apex, and it's a location, to the array element value here. And the reason we're doing this is because for each array element, we want to compare it to the last to see if it is higher up. And if it is, that's the new apex. And by the time we're through, we'll have figured out which one is highest. But when we are on our first one, there's nothing to compare it to. So we're just going to say, so if we're on our first one, set to the current apex to the array element. And this apex will not be the apex that anything else sees, because the local variable, and we're going to output our apex once we've completed this loop from our function, so our actual apex variable won't transition through the different locations until it finds the apex, which is important. So remember to make this a local variable so that it's only used inside of the function. Now, if this is false, we're past our first array element. So I'm just going to grab a reroute node to keep things tidy. and I'm going to get a branch. And I'm not going to worry about the condition yet, but true, if it's true, we're going to set the apex again to the array element value. And it's going to be true if the z of the array element is greater than the z of the current apex. So what we can do here is we can drag off from array element and get a break vector. I'm going to duplicate it, and I'm going to get our local apex. I'm going to check if the z of the current location is greater than the z of the apex, and if that is true, we're going to change the apex so that it is false again. Now, once this is completed, we have our apex location, and the first thing I want to do out of 2, so I'm getting a sequence, is print or draw our debug sphere. I'm going to move the node that I disconnected down, plug it into then 0, and the center is going to be the apex. Now, if we compile and play, it will put a sphere, it'll draw a sphere at the apex of our jump. Now, we need to figure out where the ground is at and where our feet are going to land. And that is what we're going to do with then 1 on our sequence. I'm going to duplicate everything here that's plugged into along with our predict projectile path by object type node. I'm going to didn't copy it. I'm going to paste it. Then 1 will get plugged into our predict projectile path by object type. And this velocity, the z in the make vector, is going to be set to get gravity z, which is a pure function of the character movement component. Now, what I'm going to do, and you might think, well, we want to get the last one, that's going to be where it hits the bottom, and that should be last or out last trace destination. And it actually isn't. I'm not sure why this is, but when I try to use this, I don't get the results I'm looking for. So I'm going to get a for each loop from out path positions. Actually, I don't need the for each loop. No, I do. Sorry. I'm going to get the length of our out path positions. And if the length minus 1 is equal to our array index, then we're going to set our array element to be our our land location. And the reason we're doing this minus 1 here is because we get the length of this array, and it's an integer that says, let's say we have an array of 3 things. We get the length, that's going to give us 3. Well, with the for each loop, the index doesn't start at 1 like length would. It starts at 0. So to match these up, we just have to subtract 1 by length to make the 1 be 0, 2 be 1, so on and so forth. So if this is true, if this is the last trace, the final trace, I'm going to draw a debug sphere again so we can see. We will get to our outputs of this function. And I'm trying to draw a debug sphere from our boolean. I need to get a branch, plug that into a loop body, and I'm just going to copy our draw debug sphere from over here. I'm going to plug center into array element. And the reason I'm doing all of this drawing is because so that you guys can visually see what's going on here. And something is not happening correctly. Let me see. We're getting the current actor location for start position of our second trace instead of apex. And we are done predicting our apex before our character reaches our apex. So I'll compile that. I'll change that, compile that, and now we land. We slide a bit because of friction, but we land, or the low friction, I mean. But we land right where that sphere is at, pretty much, and that's as close as we need, because that is where our capsule touches the ground. So there's a problem. And that problem is, well, the apex is where our pelvis is at, not where our feet is at. Not where our feet are at. And so this is dealing with actor location, which is at the pelvis, and I don't want to, say, okay, get the actor location, now subtract the difference between the pelvis and the feet to get this actual variable that's the distance and all of that. And it's easier just to raise this, I'd have to use that value to offset the apex, and then I'd have to use that value to offset things when I'm getting the direction. It's easier just to offset this landing position once, and everything's a bit simpler. So that's what I'm going to do. So I'm going to move this draw debug sphere over a bit, unplug this vector value that's going into center, gonna break the vector, gonna make a vector, plug the return value into center, x into x, y into y, and give myself some more room to work with. And the z of the make vector is going to be the difference between the z of the break vector and the scaled capsule half height. Now, something isn't right. It is not printing our... Oh. It's not going to be the difference. It's going to be... we're going to be adding these together, not subtracting them. My mistake. So now, we're drawing a sphere at our apex and at our landing position, which means that we have a location for our apex and landing position, which means we can compare the position of our character to the apex and landing location to then get our distance. And again, I don't really need to get the distance on 3 axes. I just need to get it on 2. Not on 2, on 1 on the Z. Because the jump animations we'll be using in the next video only care about the Z. They don't care about X or Y. So there's no reason to store anything as a distance, or to do any of our calculations with things that we're not even going to be using. So we have all of this done, all of this completed. So I'm going to drag out from this completed for this for each loop, and I'm going to get a sequence. I'm not sure if I'm going to use it. I'm just getting it here so I have something here to drag out from to wait here while I create a new local variable. And this local variable is going to be landing location. And it's going to be a vector. I'm going to set landing location before I draw this debug sphere. And there's another thing I want to do, if you make functions and you have them drawing debug things, what you can do, and what I like to do, is I like to give myself an input that's a boolean. I'm just going to name it debug. And then before I do any print to screen or debug, I can just get that debug boolean, that input. I should just be able to pull it up here. No, so I'm going to make it a local variable, which is going to be debug. Alright, I'm going to name it. Won't let me pull it up. It says it already exists because it's an input. So I'm just going to name it debug with a question mark. I'm not sure why it's not letting me just search up debug and place it as a variable. Usually you can do that. It lets me know why, if it's a glitch or if it's actually something I'm doing wrong here. Let me know in the comments. Now with this debug, I'm just going to drag it out. And I'm going to drag out from it and get a branch. To do this with both of our draw debug spheres, I'm just going to gate it with this logic that says if debug is true, draw the debug sphere. If it's false, just don't do anything. And so if you want to stop debugging, you just have to change that to debug variable. You could go, even more in depth and add another layer onto the onion by making another global character debug value, or even more global project-wide debug value, and plug that into your debug here. But for now, I'm just going to tick that as an option on the function. Say yes, debug. So now we jump, we have our stuff. If I uncheck it, we don't. A nice little feature to have. I can do the same thing. I could do the same thing over here and create a global visible editable from the editor over here on the side in the details panel debug variable, but I'm not going to worry about that right now. It's just a little something I wanted to show you all. Now, back to business here. We want to output as a return value our distance from these 2 points. So I'll drag out from this sequence for now, might get rid of it, and I'm just going to make a return node, 2 return nodes. I guess just one with 2 outputs. Yeah. Both of these outputs are going to be floats. First one is going to be apex distance. Actually, we're only doing this once, so we want to do our calculations elsewhere. I'm sorry. So we're going to output our locations. Gotta refresh this. So, no sequence. I'm just gonna get a output node. Oh, grab the wrong thing. From completed, I'm gonna go to output. Gonna add another output. They're gonna be vectors. This is going to be apex, out, and landing location out. I'm actually going to say apex location out. And now we're going to use our local variables, our apex, and our landing location. Compile and save. And now we have our predict jump arc function. And this video, as of right now, before I cut things out, is 27 minutes long. I don't want to keep you all here for too long. So I'm just going to finish up the calculations in the next video, and we'll get into the animation blueprint in it as well. Alright everyone, I hope you found the video useful. I hope you enjoyed it. If you did, be sure to like and subscribe and hit the notification bell. Thank you for watching, and I will see you all in the next video.